Okay, here's Pelea's problem 4.8. And this one asks us to show that for a symmetrical slab waveguide, the NA, the numerical aperture, is about equal to 2 square roots of 2 delta, where delta, unlike some of the earlier problems, is our index difference of n1 minus n2 all over n1. And here we're in a symmetric slab of index n1 surrounded by cladding of index n2. The numerical aperture we can derive, and I'll derive it here as I do this problem. NA is the square root of n1 squared minus n2 squared. We keep on seeing the same term. That is the numerical aperture, and we can derive that by looking at the edge of the waveguide. Sorry, my drawing's not so great. Okay, so here's our slab, N1. We have cladding around it, N2. And we have air out here. We have an index of 1 out here. And we're going to look at the ray coming in. And we're going to let this ray strike the surface, come in at some angle, alpha. And we're going to have it refract in and then strike the top surface right at the critical angle. Okay, so here's your normal to that interface. And let's see, I can call this one, for the moment, let's call this one phi. Okay, so 1 by Snell's law times the sine of alpha is equal to n1 times the sine of phi. And because phi and theta critical are complementary, that is, they add up to 90, the sine of phi is equal to the cosine of theta c. Okay, the sine of 90 minus phi is equal to cosine. Okay, so theta c, though, is given by the sine of theta c is n2 over n1. Okay, and what we can do is we can make a little triangle. We've done this in class. Boy, this is not a very good right triangle. Here's a better right triangle. And I can make a right triangle where I have theta on it here. And if the sine of the theta is n2 over n1, that's the opposite over the hypotenuse. And so by Pythagorean theorem, this is the square root of n1 squared minus n2 squared. And so we can write that the cosine of this angle is the adjacent over the hypotenuse, the square root of n1 squared minus n2 squared all over n1. Hope you can read that. And so sine of alpha is equal to n1 times the cosine of theta c, and from this equation, n1 times the cosine theta c is equal to this square root. And so we can go right up here and write that this is equal to the square root of n1 squared minus n2 squared. Okay? And the numerical aperture is the index times the sine of the angle. So it is 1 times sine of alpha. And so this is the square root of n1 squared minus n2 squared. Okay, so that's the derivation of the exact value for the numerical aperture. Now let's look at how we get that being the square root of 2 delta approximately. We'll do a new page here. Okay, so NA is equal to the square root of n1 squared minus n2 squared. If I can draw straight, it would help. What we're going to do is we're going to start with delta, which is n1 minus n2 over n1, and we're going to write that as n2, we're going to solve for n2, is equal to n1 minus n1 delta, right? And so n2 squared is that thing squared. Why don't I factor out the n1 here, and I get a 1 minus delta. And therefore n2 squared is n1 squared, 1 minus delta squared, which is n1 squared, 1 minus 2 delta plus delta squared. But if delta is small, then delta squared is really small compared to either delta or 1, and so this is approximately equal to n1 squared, 1 minus 2 delta. And so that's the trick, is to get rid of the delta squared term here. And now all I do is I say, okay, the numerical aperture, let's write now n1 squared minus n2 squared, the thing underneath the radical sign of the numerical aperture. And let's just write this using this approximation for n2 squared. So it's n1 squared minus, now n2 squared is n1 squared, 1 minus 2 delta. And so you can see we get a cancellation here. This is n1 squared minus n1 squared plus 2 delta n1 squared, which is equal to 2 delta n1 squared. And so delta, and so the numerical aperture is the square root of n1 squared minus n2 squared is equal to, this is an approximation right here, is approximately equal to the square root of this thing here. Square root of 2 delta n1 squared. Well, let's take the n1 out, and I get n1 square root of 2 delta. And that's what we're after. So we're done. And again, the whole trick is to get it so that we are squaring the delta and ignoring that term.